In science, both experiments and theory are equally important, but our science education does not give much importance to experiments, mainly because of lack of equipment. Science experiments generally involve measurement of physical parameters like temperature, pressure, velocity, voltage, current, and so on. And mostly these measurements are done by dedicated instruments. Like if you want to measure temperature, you will use a thermometer. And if you look at a thermometer, for example, say digital thermometer, it will have say one sensor element that will convert the temperature into a proportional voltage, and there will be some electronics inside that will convert this voltage into a form where it can be displayed. So that you have a display and some circuits for processing the signal and your sensor. This way, for every parameter you will have dedicated instruments. Suppose you want to measure velocity, you will have another equipment. So, this way it gets costly, but there is another way of doing this is you somehow connect these sensor elements to a computer, so that your processing and display part can be taken care by software. This makes things much more flexible and cheaper, and today we will be explaining a device that is called expeyes. It stands for Experiments for Young Engineers and Scientists, and this device is developed by Inter-University Accelerator Center, that is a research facility of UGC, and it is completely in the open domain. That means, the hardware, software, everything is freely available. It is all on the website, and there is permission to manufacture the device without any royalty or any other restriction, and currently it is available from several vendors in India and abroad, and the cost is very low, it is very affordable. So, today our objective is to explain this device and see how we can use this for doing several experiments. So, now coming back to the technical details, here you see the device, and on the top panel you see there are several connections. They are screw terminals, you can attach wires to that, and this is where we connect the sensor and control elements that we use for making measurements. So, first of all, let us have a look at these terminals, all these signals coming. So, here you see there are total 18 terminals, 9 on one side, 9 on the other, and let us have a look at it one by one. On the 4 corners you can see here the ground terminals, all 4 corners. They are at 0 volts, that is our reference point. So, all other voltages are measured with respect to these points. And then you see here there is 2 terminals marked as A1 and A2, and they are input terminals, as the arrow shows that they are input terminals, and they can measure voltages in the range of -5 volt to +5 volts. And we also have another 2 terminals here, you can see in 1 and in 2. They are also measurement terminals, but they can take a voltage in the range of 0 to 5 volts, but they have some additional features, like in 1 is capable of measuring capacitance, and also in 1 and in 2 can measure digital signals, like as applied voltages, the logic state can be measured. So, to start with, let us see how we can measure a DC voltage, for example, a voltage from a battery using this. So, we need to do 2 things for that. First of all, we have to make the connection. So, we will make the connection between ground and A1, so that we can measure the voltage, since A1 has the capability to measure the voltage. Afterwards, we have to use the software or the computer program to complete the measurement. We have to use some graphical user interface that is written for this purpose. So, let us make the connections first. To make any connections, first of all, you have to loosen the screw terminals and insert a wire into that, like here. Tighten it. So, now we have connected one wire to the ground terminal. Actually, we have connected a crocodile clip The reason is now subsequent connections we do not have to remove this, we can just connect it to this. So, let us connect to one more clip on A1. So, we made 2 wires. Now, let us have a look at the software required. Here you can see we start the applications science, from there the expeyes junior, the program is started. You can see the graphical user interface, and this program will run on any operating system that has a Python interpreter, because the whole thing is written in Python programming language. So, here you are seeing it is running on a Linux system, it will also run on Windows. So, what you are seeing here is a screen where you can plot a graph, it is a plot area, and on the side here you see A1 and A2 are listed, and also in1 and in2. So, all the input sources are listed on this left side. So, to measure A1 we should just click on this. So, it's nothing is connected. So, we are seeing a voltage very near to 0. So, now let us connect the battery. So, we have a 3 volts, say 2 1.5 cells connected in series in a holder, and we are going to connect them here. So, one end is connected to the ground terminal and other one to A1. And now, we repeat the measurement here, say click on A1, you can see it is showing 3.22 volts. The same thing we can do probably on in1 also. So, this is how we measure the DC. But as you can see, if you really need a DC for an experiment, you do not need to use a battery. expeyes has a built-in voltage source. Here you can see it is marked PVS, that is programmable voltage source. Through software you can set the voltage at this point anywhere between 0 and 5 volts. So, we can verify this. We will connect another wire here, say to PVS. So, instead of the battery, now we are connecting this PVS to like this to A1. We have made the connections. Now, if you go and do the measurement, it is not showing any voltage, showing 6 millivolts. Let us set this voltage. Here you can see right side of the window it says a set PVS equal to. So, let us put some value here. So, let us put say 3 volts or put something like 2.5. You type the value and press the enter key. So, it says already it sent the message, it has sent this, set the voltage to 2.45, almost 2.5 volts, and we know that it is connected to A1. Now, go and click on A1, it measures it. So, that means here you can have a voltage measurement as well as a voltage control. So, what we have done so far is we have generated a DC signal using expeyes. We also measured a DC signal using expeyes, that is generated internally also from an external source. Now, we will see how we can measure an AC voltage both from an external source as well as from an internal. So, we have measured a DC voltage using expeyes, and also we have generated a DC voltage. So, the measurements are done using an external voltage as well as an internal voltage. Now, we will see how we can measure an AC voltage. So, we will use an external AC source and make the measurement first. So, let us use this AC source. You can see here it is a small circuit which gives a around 70 hertz 3.5 volt AC on these 2 wires. So, we will connect one terminal to ground and another one to A1. So, you see there is a line here, and if you start measuring the voltage at A1, see every time you measure it is showing different voltage, because it is showing the instantaneous voltage. So, and the AC means the voltage keeps on changing. So, looking at like this or measuring this does not make much sense. what we have to do is we should plot a graph. So, here it is already doing it, but let us change the time axis. So, this horizontal axis we can change the milliseconds per division. Now, it is totally 1 millisecond. Using this slider we can change it. So, now you can see I have made that total 50 milliseconds. So, within 50 milliseconds you can see here around 4 cycles are there. So, this is how you can get a complete information about AC. Now, if you see one cycle how much time it takes, if you click here it says around 13.3 milliseconds. But if you want to measure the frequency of this AC accurately, what you can do is move this CH1, you drag this to what is written here fit. What it does is it mathematically compare this with the equation of the sine wave and extract the parameters, the amplitude and frequency. You can see it is displayed here 3.85 volts and 74 hertz. So, now you have seen how to measure AC voltage using expeyes. We used an external source of AC to do the measurements. Now, instead of the external source, now we are going to use the built-in AC generator of this box to make the same measurement. Here you can see there is a terminal marked as sine. It is a sine wave generator, that means there is an AC output from here. So, what we will do is we will connect a wire here and measure that. See, we have connected a wire to sine and now connect that to A1. You can see the connections are made. Now, if you look at the screen, you can see the waveform is there, but the frequency this time is 147.4 hertz. So, that is a different frequency signal. Now, let us see how we can use this in1, this terminal for measuring capacitance. What we will do is we will just connect a capacitor from in1 to ground and try to measure it. Here you can see we have used a parallel plate capacitor, just a homemade one. There is a polythene sheet and aluminum foil is pasted on both ends. It forms a capacitor. So, that is connected from ground to in1. Now, to measure the capacitance, coming back to the screen, you just click on measure C on in1, this point. It says the value of the capacitance is 312 picofarads. So, this is how you measure capacitance using this device, and this point can measure capacitance in a very low capacitance, something like up to 10,000 picofarads it can measure. Higher values, there are different ways to measure it. Now, let us see how we can measure a resistance using this. Here you can see there is a terminal marked as CN. This terminal is meant for measuring resistive sensors. You can connect a resistor from here to ground and we will be able to measure the value of that resistor. So, again we will make a crocodile clip connection here, so that we can try different values of resistors. It's done. Now, we will connect a resistance between here and ground. Say one resistor is connected between this, like this, and to make say measure or it says it is 3016 ohms. So, this is how we make the resistance measurement. Now, let us try another resistor. It should be near 1000 ohms. It is 1002 ohms. So, this is how you measure this unit for measuring resistances, but remember it can measure resistances within a limited range, something like 100 ohms to 100 kilo ohm, that you can try out leaving it open and asking for a measurement. Here you can see the error message, resistance not in the 100 ohm to 100 kilo ohm range. That means only within this range it can measure the resistances. Higher other values we can measure indirectly. Let us have a look at the next terminal, that is SQR1, and there is also there an SQR2. These two terminals can make square waves. That means you can make this voltage go from 0 to 5 volts with a programmed frequency. The frequency can be changed from 0.7 hertz to 200 kilohertz. The difference between these two are the square one has a 100 ohm series resistance, so that you can directly connect an LED to ground from here. So, let us try to use this square one and see how we can set a square wave on that. So, let us connect a crocodile loop to square one. And for testing purpose, we will connect an LED, a light emitting diode, to this. Say from ground to square one we are connecting an LED, you can see here. Now, we will go back to the screen and try to change the frequency of this. Say here you can see there is a field, I can set the frequency, I will set it at something like say 3 hertz. So, enter the frequency value and check the square one. You can see that it is blinking at 3 hertz, and using the slider also you can change the frequency. See, when it is blinking at a higher rate you cannot see that, and you can also set it to say 0 hertz. If you set it to 0 hertz, it will be permanently on, and if you set it to say -1, it will go off. That means the square one can be either set to 0 volt or 5 volts. That means by setting to a negative frequency or 0, any non-zero, I mean positive value between say 0.7 and 200 kilohertz will set that frequency on it. So, this can be easily seen by connecting a piezo buzzer to that. If you connect a piezo buzzer like this one, then if you apply a frequency to the voltage to this, it will make this sound. So, let us connect the piezo buzzer to this point from here to ground. Now, whatever frequency you set here, you will hear the sound of same frequency from here. Now, you can change the frequency, say here. You can see the frequency changing, and the frequency of the sound also is changing. And if you notice that around 3.5 kilohertz, the value is shown here, the sound becomes maximum. That is because this piezo's resonant frequency is around 3.5 kilohertz. So, one use of the square one is to perform experiments, sound experiments. So, you can use this as a sound source with a specified frequency, and square 2 and square 1 can be set to different frequencies, and that can be used for performing experiments like interference of sound and so on. Now, we will see another aspect of, suppose we have seen how to generate sound, but suppose if you want to capture sound, what we can do. If you see on the side here, there is a built-in microphone. You can see here there is a built-in microphone, and this microphone output is amplified and is connected to this terminal inside called mic. That means, the output of this microphone will be available on this terminal marked as mic. So, if you make some sound near this microphone, we can see that output here at the mic output. So, what we will do is we will take the mic output and connect it to A1. Say connect a wire to this mic output. and we will connect that to A1. And again we will use this piezo buzzer as a sound source. So, now if you generate sound, the captured sound will be available here. So, it is making some sound, and if I take this and bring near the microphone, you can see the output of the microphone there. And not only that, it measures the frequency. You can see here 3.2 kilohertz, the frequency is measured. So, not only the output of this one, if you have an external source of sound, suppose a whistle or something, the frequency of that also can be measured using this microphone. So, we will use an external source of sound, like this another buzzer, and we will power this by using our this 3-volt battery. You can see it is our external sound source. So, it could be a tuning fork or anything. Now, we just keep it here. So, you see that on the screen it says the frequency of the sound source is something like 5.5 kilohertz. So, we have seen now how to perform experiments in sound, some of them using expeyes kit. Now, we have some more signals here to be explained. One is marked here as OD1, that is a digital output. That means, software can set this terminal either to 5 volts or 0 volts. So, we will see how to test it by connecting a something to this. We will connect that to in1 and measure the voltage. So, we will use a piece of wire to connect this OD1 to in1 here. Now, let us measure what is the present voltage at in1. So, you click on in1, it is at 0 volt. Now, you come on the right side, it is written here set state and OD1. So, if you click here, so now you are setting this OD1 to 5 volts. We will go back and measure again, it says it has gone to 5 volts. Suppose the wire is not here, then that voltage will not reach here, right? Or you can see, suppose you put off this OD1 and again measure, it has gone to 0. So, its OD1 is a very simple feature, either this terminal can go to 5 volt or 0 volt, but it is a very powerful feature when combined with other things in several experiments. So, we have covered almost all the terminals, the hardware description of the device.